Now we are going to discuss about composition of complex determination by using two methods. One is Jobs method, other one is mole ratio method. There are two methods to find out the composition of complex forming when metal and ligand are going to react. So there are two methods. One is Jobs method, very important method. Other one is mole ratio method, that is also very important. Now in these two methods, the concept is same because they are going to find out the formation of complex, that is stable complex. How many ligands are required to combine with a metal? Maximum how many ligands will combine to form a complex? Because we don't know how many ligands will be able to combine with one metal, right? That we have to identify by using some method. So that for that one, these two methods came into picture. The first method we are going to discuss now, Jobs method. This method is also called as continuous variation method. Why we will call it as continuous variation method? Because we are going to take metal and ligand in some ratio, and we are going to vary this metal and ligand ratio while forming the complex, and so it's called as metal continuous variation method. And the principle in this method is very easy to understand. The mole ratio of the metal ion and the ligand is varied between 0 to 10. What does that mean? We will take some amount of metal and some amount of ligand. This mole ratio will vary. This mole ratio this mole ratio will vary from 0 to 10. And while changing that mole ratio, we'll observe how the absorbance is changing. How the absorbance is changing, that one we will measure while changes this mole ratio from 0 to 10. And whichever is going to give you maximum absorbance, that is the stable complex which is forming. That's what Jobs method is going to tell. So how the complex is going to form? We are going to change the mole ratio of metal and ligand based on the absorbance value. We are going to find out which is exact composition of metal and ligand actually, right? And now we are going to take C as a concentration of concentration, that is combination of concentration of ligand and concentration of metal. Now this is a procedure to be followed. In general, there is a practical experiment also is there in this Jobs method, and here the absorbance is the main criteria which is going to give us the main information that which is the exact composition of the metal ligand forming. The absorbance is the then, so we are going to take a graph between absorbance versus the mole ratio of metal and ligand. The maximum absorbance will give you the composition of the metal ligand forming here, and here absorbance versus mole fraction of the ligand we are going to plot. Based on the graph we are going to get it, right? Now in this one, what we will discuss about procedure later. First let us discuss about the concepts which are there in this particular one. In this one, only one complex is going to form because we are going to vary metal and ligand. We are not going to enter into different ligands or different metals. One metal, the ratio we are adding, one ligand, the ratio we are adding. As both are going to form one ligand, one complex only, this is restricted to one complex only. If only one complex species has been formed with the composition of M and Ln, and the absorbance is measured at a wavelength, the complex absorbs different wavelengths. It will absorb because we are varying the different compositions, right? And here the main answer we are going to get it is here N, because N is the one which is going to decide how many ligands are going to combine with metal to form a MLN ligand. So the composition of M and L depends on this N. This N is going to be determined in this particular Jobs method, where N is equal to X maximum by 1 minus X maximum, where X is representing the mole fraction. The average number of ligands bound by one metal ion can be found out by using this method, right? Calculated from the abscissa of the maximum of the curve. We are going to show you the graph. Based on that graph, we are going to get an answer from here. So maximum N is equal to X maximum divided by 1 minus X maximum. What is this X and all we are going to see here in this particular topic. So this is very common method for the determination of composition of a complex. The jobs method is very common and very easy to identify also. Even practical also we can do it very easily, this one. And here if you are going to the procedure, right, equimolar mixture of metal and ligand are taken or mixed given in a series of solutions having the same total concentration of metal and ligand. So here what we are going to do, metal and ligand we are going to take and we are going to vary the composition, but we are going to keep the total volume as constant. Let us discuss like this. For example, if you are looking into, right, in a test tube, we will take imagine up to here 10 ml. We will take first 0 ml of metal or 10 ml of metal, 0 ml of ligand, metal and 0 ml of ligand. In this same test tube, what will happen? In the same test tube, up 10 ml, we will increase the metal ligand number as 1 ml. This is 9 ml. Same way, test tube number, next test tube. So we will take a series of test tubes in which here up to here we will take it so that it will be it looks uniform actually, and 8 ml of metal and 2 ml of ligand. So we will keep on taking this one till here. Here if you are taking test tube, right, and here up to here how 0 ml of metal and 10 ml of ligand. In this way, we will vary the mole ratio of metal and ligand, but the total volume is constant, that is 10 ml. So like this, we will prepare a different solutions and we will see how the absorbance is varying from solution to solution. Based on the variation of absorbance along with this particular one, we will draw a graph. From there we will get the n value, that is x maximum by 1 minus x maximum. So look at this particular one. This method is going to determine the composition of the complex and mainly used for solution where only one complex is formed. Already we have discussed, we are going to vary metal and ligand only. We are not including any other metal. We are not including any other ligand also. So it is going to give you only composition of M and L at different ratios. At different ratios is going to give. It is not going to give in a different complex here. It is going to give ML only at different ratios. As ratios are different, the obviously absorbance will be different. So absorbance versus this ratio will give you the graph, right? And now procedure. Take 10 solutions, a series of solutions in which, as we discussed just now, take in one test tube, take 10 ml of metal. In second test tube, 9 ml of metal, 1 ml of ligand. Just like that, keep increasing ligand and keep decreasing the metal. So the volume is going to be 10 ml, that is going to be uniform. And here already we have discussed C, that is total concentration is equal to concentration of ligand plus concentration of metal. So concentration of ligand is going to indicate with Cl, concentration of metal is going to indicate with Cm. So here Cl plus Cm is equal to constant and there's ratios are changing. Ratios are changing, but total volume is same. And here we can see here it is metal plus ligand. This is Cm if you are taking, this is Cl if you are taking, this is Cm plus Cl. You can see here all are 10 only. That's what we mentioned, the Cl plus Cm is equal to constant. Here what we are varying? We are reducing the volume of metal from 10 to 1. The same way we are increasing the volume of ligand from 1 to 10, but we are making the constant volume, that is 10 ml. In this way we are going to make some different solutions with equi volume but different concentrations of metal and ligand. Now once after taking a different test tubes with different ratio, this is going to be 10 only. This is going to be 10 ml only, but ratios are different. 9:1, 10:0, 9:1, 8:2. The ratios are different till 0:10. So in this way, we will take solutions and we will measure absorbance by using instrument, right? Once after measuring the absorbance for different mole fractions of ligand, what is the meaning of mole fraction? Mole fraction means what? Mole fraction is equal to concentration of ligand divided by total concentration. Concentration of ligand in total concentration of what to call metal and ligand is called as mole fraction of ligand. So we are going to take mole fraction of ligand and absorbance. If we are going to plot a graph, how it will look like? It will look like this, right? And if you are taking a line here, right, this is maximum. And if you are extending this one, right, this will give you maximum. And this is the place, I hope the graph is very clear. This is the place it is going to give you the maximum absorbance. Maximum absorbance. This maximum absorbance is the place where ligand is forming complex with exact composition. That is going to give us the composition of the, that is going to give the n value. N value, that is how many number of ligands are exactly attaching with the metal, can be understood this particular maximum absorbance value, right? Here measuring the absorbance by using spectroscopic meter, because without doing this experiment, right, we cannot get these values. This is a practical experiment. So we will measure, imagine after preparing in test tube, right, we will see and we will pass a light and how much light is absorbing by this solution, that is called absorbance. So the absorbance will be recorded in the spectrometer. From there we will record the value. So based on that value, if you are drawing a graph, the graph will look like this. Why? Because the ligand is going to increase, right? And maximum number absorbance will be given by the place where exactly the number of ligands are matching with the metal. And here mole fraction of ligand versus absorbance, we'll write a graph and this graph is going to be like this. Right. Now a mathematical derivation should be there in the written part because this is along with the practical exam, we can understand the theoretical part also here. So what is the meaning of mole fraction of ligand? Just now I told you already, mole fraction of ligand, that is x, because that n we have seen, right, at the starting. In the principle we have discussed about n. N means number of ligands that is attached to the metal. This n will give you n maximum divided by 1 minus x max, right? So this x is equal to what to call mole fraction of ligand. What is the meaning of mole fraction? The concentration of ligand present in the total concentration. Concentration of ligand present in total concentration is called as mole fraction of ligand. Now for a complex, we are going to take MLN complex. For MLN complex, what is the formula of N? What is the meaning of moles? Moles is equal to concentration of L by concentration of M. So we are going to get this one. We are going to get this one, right? And here by using both this one, for example, already we know that Cl plus Cm is equal to 1, right? If you are dividing with C, Cl by C plus Cm by C is equal to, what will happen? This is C, right? C by C. So Cl by C plus Cl by C means what? Mole fraction. Cm by C is equal to 1. So Cm by C is equal to 1 minus x. Cl by, let's see here, Cl by C, that is going to be Cm by C, Cm by C, x is equal to 1. What is the meaning here? Cm by C is equal to 1 minus X, right? And already we know that X is equal to Cl by C, right? If you are dividing these both, that is X by 1 minus X, what happens? For example, if you are taking this as first, second equation, if this is taking as first equation, if you are dividing 1 with 2, what happens? 1 means X by 1 minus X. Cl by C, it will be reverse C by Cm. So obviously both will get cancelled and it will give you Cl by Cm. Cl by Cm means already we will discuss now. The Cl by C means what? Cl by Cm is equal to N. That is number of ligands attached to the metal during the formation of this complex. So this N is equal to X by 1 minus X. This N is the number which will give you the composition of the ligand which is forming this one. In this way, this job method will help us to find out N value is equal to X by 1 minus X. From the value of N, complex MLN composition can be determined. In this way, Jobs method will help us to find out the composition of the complex forming here. What are the drawbacks which are there in this particular one? There are two drawbacks which are there. One is in this one we cannot use different ligands. We have to use only one complex. One complex only will be going to be used here. One complex is formed under the experiment conditions because we are varying metal and ligand only. We are not varying composition of metal and ligand only. We are not varying metal and ligand. And the second point is we have to keep the volume constant. When there is no change in the total volume of the solution containing metal and ions and ligand, we cannot change the volume. So, as both are the limitations in this particular one, we cannot use different complexes or we cannot change the volume of total volume of the complex composition, right? And in this way we can find out the composition of the complex. And now we are going to discuss about composition of metal by mole ratio method. What is the meaning of mole ratio? Mole ratio method is exactly similar to the Jobs method, but here we are going to do a small one more extra word called we are going to keep that constant amount of metal ion and we are changing the volume of ligand. We are changing the volume of ligand, but we are keeping the constant volume of metal. In this way, we are going to prepare solutions, and here also is almost same. But the compositions we are varying, we are not changing both together simultaneously. We are taking one as constant, and we are increasing the what to call volume of volume, or obviously if you are changing volume, concentration will vary, concentration of ligand. So in this method, a series of solutions are going to be prepared, not in a test tube, but it's going to be prepared, containing a constant volume of metal ion and varying amount of the ligand, keeping a total volume constant under identical conditions. We are keeping the conditions same and just ligand we are varying. And for example, 5 ml of metal ion. We are adding 1 ml of ligand, 2 ml of ligand to this metal. For example, 5, 7, 8, 9. So we are keeping that metal constant and ligand we are varying. And what is going to happen if you are drawing which is constant? Metal is constant and ligand is varying. So, but the overall conditions we are maintaining same, and the absorbance of these solutions is measured and plotted against the ratio of the moles of the ligand. How many ligands, ratio of the moles of ligand if you are taking it, right? So the graph is going to come in this way. So if you are taking this absorbance and NL by NM, right? Ratio of moles of ligand to the ratio of moles of the metal, if you are taking this composition versus this composition, that is the absorbance composition, will give us a graph. Now the graph is going to be like this and here it is going to be constant. and the absorbance will keep increasing here, because if you are in general it will be like this. If you keep on increasing the ligand more, what happens? If you increasing the ligand, the absorbance also will increase. So this point will give us the point composition where exact number of ratio moles of ligand reacting with the metal, right? This break point, this is the break point. This is the break point will provide the composition of the complex. So almost both are same. Here, there we are varying both. Here we are keeping one constant and other ligand varying. And we are going to draw the graph there. That graph is very clear. That graph is going to come in this way. And this graph is going to be like this. And this break point will give us the mag composition. Here, the maximum absorbance will give us the composition. Nothing else. Just the preparation of solutions is different, but the method is going to be depending on the absorbance only. Of course, absorbance versus NR by M here, there also absorbance is going to give us the maximum composition which is going to be formed. In this way, spectral method will help us to find out the composition of the metal which is forming here.